Okay, Bismillah ar-Rahman ar-Rahim. In this video, inshallah, I will be covering the hash data structure, which is kind of substituting the class that I missed. So let's start just by a very quick review. What we have covered in the class so far is the following. Just as a quick reminder, we in this course so far have covered several data structures. If you recall, we started first by saying that we have studied the array data structure in the previous courses, such as in the C and C++ courses, and we have seen that this data structure is very simple to use. That's one of the main advantages of it. And at the same time, it has other advantages, such as the ability to do direct indexing, which means we could quickly go to a value by its location, and also the concept of caching locality, which can speed up data retrieval in certain cases. Now, array, if you recall, has a major limitation, which is it doesn't have the ability to grow and shrink at runtime. It's fixed size. You define it by a specific size. If you want to grow it, you have to do like define a new array, copy all values to the new array, and this will cost you order n. Now, we also have studied, if you recall, three types of lists. The list data structure, if you recall, we studied it so we can kind of go over, I would say, the limitation that array has, which is basically the fixed size limitation. So we studied three types of lists: the singly linked list, the doubly linked list, and the array list. Now the array list is pretty much similar as far as I would say limitation and drawbacks to array with respect to the fixed size. It will cost you order n to grow and shrink, as we recall, if you recall in the past. Now the singly and doubly linked list are two data structures that will allow you to grow and shrink dynamically at runtime. So we do not have the same issues that we have in array. So that's one advantage of singly and doubly over array. And at the same time, they do have the limitation where you cannot do direct indexing. So that is a major limitation of singly and doubly linked lists compared to an array. So algorithms such as binary search algorithm cannot be applied accordingly. So this is like it's a trade-off between these two types of data structures, and that's why we then studied a different data structure, which is, if you recall, binary search tree. Now, in the binary search tree data structure, we have seen that we can somehow combine the advantages that are coming from array along with the advantages from the linked lists, whether singly or doubly. And by that we mean we can at runtime grow and shrink the structure, adding or deleting data without reserving extra space, and yet achieve fast search that is similar to binary search that's done on an array. Of course, there are conditions for this to be achieved. If you recall, must be balanced. We have seen that we can achieve balanced binary search tree if we use one of the options available with binary search tree, such as the AVL trees, which we studied in class. Now, we also have studied, I would say, special data structures. If you recall, we have studied the so-called queue, and also we have studied a stack. Those are called special data structures. They have special use. They are data structures that are used in case if you want to control the data entry and exit from the structure based on time of arrival. So if you recall, the queue supports what we call the first in, first out, while the stack is the last in, first out. So it's based on time of arrival of data. Here, the first that comes into the queue is the first one to leave, while here the last one comes into the stack will be the first one to leave the stack. Now, so those are two special data structures. Also, we covered also a special data structure called priority queue, and the priority queue is kind of different than this queue, where the concept of priority basically is there to control the way how data is actually going to exit out of the queue. It has a special use, and we have seen that we have a min-based priority queue and max-based, and also we have studied 3 different ways to implement the priority queue, and we said the most efficient way is heap, and the heap allows me to do enqueuing and dequeuing, if you recall, log n operation. The priority queue is a special data structure that is used in case if you want to do enqueue and dequeue based on a priority, either min-based or max-based, and the heap is the best way to do such a data structure. So this is just in a nutshell so far what we've done in the class. Now, in our session now, what we will be discussing is actually a new data structure, which is called the hash data structure. So this data structure is similar to, I would say, ArrayList, bounded search tree. It is a general purpose data structure that will allow fast insert, delete, and search, and search by value, and under a specific condition. We will see what those conditions are. So it's a general purpose data structure, very much common in the different programming languages. All modern programming languages support hashing and hash data structure. Of course, the word hash has lots of applications. Here we're looking at it from programming perspective, programming languages perspective. Now, in the world of security, the word hashing is so common. Of course, at the end, we're talking about the same functionality, but here we're looking at it from the perspective of how data is getting stored using hash functions, while in security it has a total, I would say, different use and different perspective. So we're not discussing this in here. We're focused on how we use hash data structure in the class. So I just wanted to give you in a nutshell the kind of data structures we covered in this class, so you be aware of them. And if you, just as a reminder, we have studied how we can implement all of that, taking the code in C++, so you should be able to do all of them, and we will conclude all our data structures with the last one, which is basically the hash data structure. Okay, so let's proceed. Now, before we proceed, we have the code of all our classes already online, as you know. So this is the hash data structure code. I will be explaining this in detail. And as you can see, I'm using DLL, including the DLL library header that we did in the past. And the hash class, here it is. This is the header, the prototype, and here is the implementation of this data structure. So let's first get into the concept of hash before we come into the code and look how each function is actually implemented. So let's proceed and go and look at that. So let's start. Now, when we say hash from our class perspective, the hash is actually a simple data structure. We are talking about, we have seen that doubly linked list. Now, the doubly linked list is a data structure where it allows you to track nodes, and those nodes are interconnected, where there is a head node and there is a tail node. Now, the interconnection, you're familiar with it. I'm not just gonna go over that until, so this is the tail and this is the head, for instance. This is the doubly linked list. Now, the hash, what it does, it's actually, it takes this concept of DLL and builds upon that. So what we have is, we have a member variable that's called data. That member variable points to an array. Now, this array is actually nothing more than a set of doubly linked lists. So in this example, I have an array that's of size 5. So the indices will be 0 through 4. Now, each one of these, we call them buckets, is actually a doubly linked list. So you would need to think of each one of these. So I have 5 doubly linked lists here combined into one array. So to achieve that, the data must be of type doubly linked list, as we do in class type T, and we will make it via a pointer. So to be able to make a dynamic array of size that I decide at runtime, I will use the pointer trick. So I will say data equal a new doubly linked list of type T, and then I specify the size, whatever that is. So in this case, what we compensate here or use is actually the size 5. So that's why it's 0 through 4. So I have an array of doubly linked lists. I am pointing to it via this member variable, which is called data. Now, what's the idea of having an array of doubly linked lists? The idea is you will be storing data inside these lists. Now, the data that you're storing, this whole thing is called the hash. So the hash is nothing more than a set of doubly linked lists, and each one of these we call it a hash bucket, and we can store value in it. Now, how do we know where exactly we will be storing data? For instance, if I'm telling you, you know what, store the following values for me: 1, 20, 21, let's say 33, let's say 13, 103, maybe let's just say 205. I'm telling you these values are supposed to be stored in this hash. Imagine the hash is a hash of type integer. So because I'm giving you integer values, and so at that point in time the object has to be instantiated with a specific, I would say, data type. Now, so which list is supposed to take these values? Now, this will be determined by what we call a compute hash function. That is this concept of hash function. So let me write it in a different color so we pay attention to it. So we have this so-called hash function. Now, the hash function, what's the, the purpose of it in this context, which is the data structure that's called hash. The hash function is nothing more than, think of it, it's a box. And say, I'm just going to abbreviate it using HF for hash function. You give it a value. And in our context, it's supposed to be returning to you the location of the index. I'm just going to say look for location or index. So whatever value I give it in here, it's supposed to tell me where is this value supposed to be stored at. So now, who decides what the hash function is going to be? This is you, software developer. You can pick whatever hash function you like, and usually when we design a hash data structure, if it's something like we have the control over, we pick our hash function carefully, and there are many factors control how you select this hash function. The nature of the data you are dealing with, the size of the array of the hash, and also you could rely on built-in hash functions that come with many programming languages libraries such as MD5, the message digest 5, or secure hashing function. But here in the context of our class, we're not going to be doing something, I would say, extremely complicated or fancy. We want to just show the concept. We will be showing to you how we could do simple hashing, and then it will be up to you later to modify these hashing functions and do whatever you like and you see fit into your application. Now, so for this case, we will be doing a hash function. We will call our hash function compute hash. I want to do the same thing as in the code. So here we will have our first compute hash function, and notice I'm going to make something extremely simple. I'm going to make a hash function that returns data type of integer. I will call it compute hash. Okay. Now this compute hash function receives a value of type integer, so I'm just going to say it receives value x, and it's supposed to be doing some logic. For instance, I'm just going to say x mod the size. Let me just fix this 1 second. I'm just going to say return, sorry for that, supposed to be returning a value, x mod the size. This is it. Very simple hash function called compute hash. receives integer value x because we are doing something for integer. It takes this x and it does the mod operation on it, and the mod will be mod size. Now, if I want to apply this in our example has a size 5. So I'm going to be applying whatever values I have here. I will be doing mod 5. Mod 5. This will be giving me the location. The location will determine where exactly which list I'm supposed to be storing this at. Notice this trick, mod 5. Why would we do such a thing? Why would we include this as part of the hash function? I think it's obvious why. Because I don't have like the option of storing data outside the array. So I'm supposed to be using locations that are 0 through 4 in this example. And the mod 5 operation will guarantee that whatever value you are giving to me will be in this range, 0 through 4. So that's the idea of why we did the mod size thing. Now, here we're taking something very simple. All what I'm doing is just, I'm taking the value, whatever that is, I'm doing mod 5, and I'm storing this in the list. So let's apply this hash function, which is compute hash, that's on for integer, on these values and just see the result. And to do that, I'm going to apply this here on the left side, and then we take it from there. So let's take these values one after the other. So let me just do that in a different color. For instance, I'm just going to use blue. So if I take the first value 1 and I be doing 1 mod 5, this will be 1. So that means this value 1 is supposed to be stored at location 1. So I'm going to do add tail. We will be using add tail on the list. So the first value added to this list will be 1. This is how the insert operation works. So if I want to insert, I want to apply the hash function, determine which list, and then just basically add it to that list. We have two options. Either we use add tail or add head. Why we use these two? Because both are order 1 operations in doubly linked list. Now, let's try the second one. The 20, if I do 20 mod 5, remember we're talking about the remainder. So the remainder of 20 over 5 is 0. So that means that 20 will go in here. Okay. Now the 21, if I do the 21 mod 5, it will be 1. So accordingly, if I'm doing add tail, it will be right after this. So this is how it functions. You just apply the mod operation and simply get the location and add it to the list, the corresponding list of that location. So let's just do the other ones very quick. So if I have the 33 mod 5, it will be 3. Accordingly, the 33 will be in here. Now we could do the other ones quick. 13 will be in here too. You could apply that. The 103 will be also in here. So the 103 will be in here. Then the 205 it will be here. Again, 205 mod 5 will be 0, so accordingly goes into this location. So see these values 2, 4, 6, 7. These 7 values you see in here have been stored into the hash in these locations. Now, what did make these locations be selected? It's just the hash function I have used. I use compute hash, and that was it. It's just take the value and perform mod size. So this is the idea of hash data structure. Very simple concept in general. Now, you might say, what is it that I'm benefiting from this operation? What are the benefits of this? Like, why didn't we do that? I think I would say the advantage will be very clear. So if you want to do this, you did the insert operations, and now you want to start doing other kinds of operations, such as search, such as delete. Imagine you are searching for the value, for instance, for that, let's say you're searching for the value 103. You already did the inserts. You have 7 values. Now, how is the search function supposed to be structured? If I want to do it correctly, I'm not supposed to search all lists, because I know how I did the insert operation, so I should take advantage of that. How did I do the insert operation? I used the compute hash. I computed the location of 103 and then I did add tail. So in the search, I'm supposed to be doing something similar. I'm supposed to be doing 103 with 5, it will be 3. So if 103 is part of my hash, it must be in this location. Now, so what advantage do I get? It's a list. I still have to do search through it. The beautiful thing here is that instead of looking through the whole thing, I'm now not going to look through location 0, 1, and 2, or 4. I'm going to be focused my search on the index 3. So in this simple example, I excluded 4 values out of 7 in my search, instead of searching through the 7 values. This by itself will speed up the search process. Taking into consideration that the compute hash function itself is just one operation. It's just like take a value and do mod size. And that's actually an order 1 operation. So the hashing, if it's not complicated process, it's not a complicated function, it will be of order 1. So big O-wise, it won't be adding a lot of like logic. So it will end up actually speeding up the search, like in this case. Now, if things are perfect, if there is, I would say, a good distribution of values, then most likely every list will have some values, and then the search will become very effective, because if I go just to one location, I will be excluding all other values, and we will comment shortly on the big O thing for the hash. Okay, so that's the idea of hash. Now here the mod operation worked perfectly because I'm doing integer. How about if I am to make a hash that is for a data type that doesn't take mod operation, such as a string? How can I deal with it? Let's look at the hash in the context of a string and see what can we do to basically make this happen. So let's look at this second example. Let me just do that, please. Okay, so imagine I have the same hash of size 5. So I'm just going to make it simple for that. Okay. So to make it simple, of course, the size doesn't have to be always 5. I could change that, as we will see shortly when we talk about programming. Now, this time I don't want to store integers. I want to store strings. Imagine I have the following string values. Let's say A. Let's say a string A, B, C. Let's say string B, 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 4 B's for instance. Let's just say C, D, C, D. And let's conclude with the 3 C's. Imagine I have these 5 string values. I want to store them inside a hash. What difference would it make? First, in this example, the size is 5. So that didn't change. Okay. Now, can I use the compute hash function we did for integer? Of course, no. Because mod operation will not work on string. So what can I do? There are so many options. So I need to design a hash function that will, same thing, will return an integer, will be called compute hash, and that hash function will receive a string. Let's say string val, I will call it. Now, one thing I could do, very simple, is just to say return val dot size. Let's get the size. For that, I'm just going to make mod size. What is this dot size thing? This is the built-in string function. The size of AAA is 3. It's the length, basically. So this will be 3, this will be 3, this will be 4, 4, and 3. So here you are saying, you know what, since I cannot use string as is with mod operation, why not to get some property of the string that is compatible with the mod operation, such as the size. The size is the length. it will immediately give me integer, and I can take advantage of it. This will work, but there is a problem with it. The problem is all strings of equivalent length will go into the same cell, same bucket. So for instance, the AAA will go in here using this model, and the ABC same thing, and the CCC same thing. This is not a nice distribution. Now, if you have, for instance, if you are using this hash function for to store names of students, we know that, like for instance, most of the students will have, let's say, first name or last name in the same range. For instance, maybe 4 letters to 9 letters or something like that. So there will be cells unused, and so it won't give a great distribution. That's why we will do something else. Like what? Let's just show you what can we do in this case. Let me write a different code. Imagine we have this. I'm just going to do integer sum. I'm going to initialize the sum with 0. So now what we will do is we will use a simple trick, is we will use the ASCII code of the string. So in this case, I'm going to be doing for integer I. I'm going to be looping through the characters of the string. I'm going to say I less than the val dot size, and then we all know I plus plus. Now what is it that I'm going to be doing is this: sum plus equal value of I minus the character A. This is the character A. I'm not sure it's clear to all of you. So what is this value of I minus A? And adding this to the sum, which is initialized to 0. We will see shortly what I mean by that. And then I will be returning sum, and to make sure the location is in this range, I will do the trick of mod size. Okay, so that's the compute hash function that can work for string, and it will give somehow a better distribution than the one we just suggested, that was just size mod the string size mod size. Now, how does this function work? Let's just take this string as an example, ABC. Now the string ABC, you need to remember that this is an array of 3 characters. Could be 4 if there is a null string, but here let's just focus on the string itself. So here I have A, I have B, I have C, and this is index 0, index 1, index 2. So this one, the length is 3. So here what I'm saying is make a loop. Sum will be initially 0, and then I'm looping I from 0, first index, all the way to the length minus 1. So I will be looping through these 3 characters. I'm taking the first one, value of 0 will be A, and I'm saying A minus A. What is A minus A? Now when you put an integer operation or a number operation in front of a character, the C++ compiler will say, okay, this operation is compatible only with numbers. And since the programmer is putting a character, so it will implicitly put the ASCII code of the character. Wherever that is, if it's capital case A or small case A, it will be either, I think, 65 or 92. Whatever that is, you don't have to memorize it. It will be taking the ASCII code and subtracting this from the ASCII code on the other side. In this case, since it's the same letter that I'm subtracting, so it will be basically storing 0. So sum will be 0 plus 0, so that's not a problem. Now when it moves to the second one, and it does the B minus A, we all know that the ASCII code of B is 1 value larger than A. So this one will be 1. This one will be 0. And then we have the C minus A. Why am I always subtracting from A? Because this is what the code does. I'm always subtracting from A. So this will be 2. So I'm adding 0 plus 1 plus 2. This will be 3. So this string will have a sum value of 3, but I'm returning 3 mod 5, so that means it will still be 3, and accordingly the string ABC will come into this location. So if I want to clean this, based on this quick explanation, the string A, B, C will go to this location. Why is that? Because 0 plus 1 plus 2 will be 3. 3 mod the size will be actually 5. Mod 5 will be actually 3. So if I apply the same logic on this one, the A, it will be 0 plus 0 plus 0. And that's because A minus A is 0 plus A minus A is 0, so it will be 0, 0 mod the size, which will be placing the triple A will be going into the first location. Now, how about the 4 B's here? We all know that this will be B minus A1 plus 1 plus 1 plus 1. So it will be 4 mod 5 will be going right in here. How about this one? We know the C is 2 and the D will be 3. So 2, 3. Why D is 3? Because D is 3 steps after A. So we know that C, as we have seen, A minus A0, B minus A1, C minus A2, D minus A will be 3. So accordingly, it will be 5 plus 5, 10. So in this case, I do 10 mod size, which is 5. It will be simply 0. Accordingly, this string, which is C, D, C, D, will go right into the first bucket. So that's how we can do a compute hash function that can work for a string. And I just wanted to show you at least one example of how we can do one string and how we can do one the other one, which is basically the integer that we have seen in the previous example. Okay, that's great. So now, okay, how can we code such a thing? Actually, before we go to coding, let's just discuss the big O of the hash operations. So let me clean this. Now, the hash data structure supports by implicitly 3 operations that we need to be familiar with. Of course, we could add more. But the basic operations are insert, search. Of course, all of them receive a value of type T, T value B, and finally the delete, T value B. This return void, this is Boolean and Boolean, and we will see those shortly. Now, what will be the big O of these operations? Now, the insert operation, it will always be of order 1. Why is that? Because the way we do the insert, if you recall, we do compute hash, which is order 1, assuming that the compute hash is done in order 1. And then we have the add tail on the list, and the add tail is also order 1, so that is guaranteed to be order 1, again, if your compute hash is order 1. Now, for the search and the delete, this is not the case. It will be dependent on the hash case. What are the hash cases? Now, the hash cases are actually 3 cases we always cover. We have what's called perfect hashing. We have a hashing with what we call uniform distribution. Uniform distribution. And then we have the non-uniform, or what we call other. Now, what is the perfect hashing case? A perfect hashing case is when you have a hash where each one has maximum 1 value. I'm just going to say value 1, value 2, value 3, at least maximum 1 value. This is called perfect hashing. Why is this perfect hashing? It's obvious that perfect because the search and the delete will be order 1 in this case. Remember, insert is guaranteed to be order 1, but here I'm talking about search and delete. If the compute hash function is order 1, so it will come to the location in an order 1 time, and since it's only one value, so it will take also order 1 to do the search or the delete if we want to achieve that. So that's what distinguishes perfect hashing, is that it gives me the best big O operation for these 3 common operations, and this is the best you could get basically compared to any other data structure. All operations are order 1. But let's be realistic. Perfect hashing as a case is not difficult. It's not I would say easy to achieve in real world, because you have a condition here that you have to have a perfect distribution of values, and also the number of values must be less or equal the size. So then here you are somehow limited in your options. There has to be a very good knowledge about the situation of data. You design a perfect hash function and select the right size to achieve such a thing, which is again not easy to achieve in I would say in real world scenarios. That's why what is more ideal to achieve is the uniform distribution. Now the uniform distribution, here what we are talking about is that the data are distributed somehow evenly across the different hash buckets. So just as an example, imagine I have 3 values here, 3 values here, 3 values here, 3 values here, 3 values here. This is just an example. I'm gonna have the data distributed evenly, uniformly over the different hash buckets. Now, what is it going to be for insert in this case? The insert is not going to change. It's going to be order 1. Why? Because I apply hash function to find the location, then I do add tail. Both are order 1. Order 1 plus order 1 will still order 1 big O-wise. Now for the search and the delete, it will depend. There is best case and worst case in the case of uniform distribution. How is it going to be? Let me put it in the front page. I will summarize here. I'm talking about uniform distribution case. If we are talking about the search, I will have best case, I will have worst case. Best case, it will be order 1. When would this happen? It will happen if I have the value that I'm looking at. In my example, I had 3 values. If it happened to be the first one, I will do order 1 and then order 1. What about the worst case? The worst case, it will search all the way to the end. But to the end, remember, it's not the whole thing. Remember, each one has 3 values. Each one has 3 values. So it will search only this bucket, and this bucket will have how many values? It will have what we call lambda, or the load factor. We use this expression, which is simply the number of elements in the hash over the size. That would be the worst case, the lambda, or what we call the load factor, which is the number of elements over size. So here it will be order of basically lambda. That's the worst case. And again, I'm talking about uniform distribution case. The same thing applies to the delete function. Best case, it will be order 1. Worst case, it will be order lambda. This is how actually it is. And lambda again is n over size. Now why is it? Maybe some of you think, oh no, it's just supposed to be n because size is 5. Remember, 5 was an example. Because size is something that's controlled by the developer or the user. So user control both. He adds values, so he controls how many n values we have, and also the user controls the size. This is something, as we will see, can be defined at runtime. And accordingly, these are 2 factors that we have no clue what they are. It could be size, could be close to n, could be very far from n, less than n, could be more than n. So that's why the whole thing is variable, and we call this the lambda or the load factor. Now the last thing is if you recall the other, there's no uniform distribution. Then the other, the insert is still gonna be a big O1, but for the search, what was the worst case that could happen and what's the best case that could happen? Remember, for other, the worst thing that could happen, I'm just gonna put it here, is you have very bad hash function that puts all the values in just one hash bucket. Imagine I have, for instance, these 6 values and all of them go into the first one. So in this case, the hash function didn't actually, I would say, bring us any benefits or advantages. It's just acting as a normal list. And I have, like in this example, I have 3 other lists reserved, but they are actually unused. And you're only focused on one list. So now you are back down to the big O of a list. So best case of search will be order 1 and worst case will be n, because all the values are in here. The same thing applies to delete. It will be 1 and n. I'm just going to put summary of that. So that's how you should look at the big O analysis of hash. Now, there is one thing worth to mention, is that we focused our talk on search, delete, and insert. Now, how does the hash function or act or perform, I would say, when it gets to functions that are different than these 3? For instance, let's just take as an example, how would the hash function if we do, for instance, add a new function, and that function, let's say, is called find max. Imagine you want to find the max. You have a hash, and the hash has values. And let's say here we have some values, here we have 2 values, maybe here we have 4 values, maybe here we have 3 values, and you're looking to find the max. Now, there is no way that you could know what the max location is using the compute hash function or any of that. The only way to find the max is you have to go through all the values. You have to scan these, and then these, and then these, and then these to find the maximum. So this will be actually of order n. So my point is, the hash does not do well always, depending on the operation you're looking at. So something like find max, find min, or anything like this that requires traversing the whole thing will end up doing actually order n. While if you recall, in the binary search tree, if it was balanced, it will be order log n. And if we talk about heap and you talk max heap, it will be also log n. If we have array that's sorted, it will be log n. If you have doubly linked list that's sorted, it will be actually order 1. So depending on the data structure, so the hash it is beautiful when it gets to insert, delete, and search, but it's bad when it gets to other operations. So that's why you have to select your data structure carefully depending on the function you're trying to use this for. So just wanted to put this note on the side so you're kind of familiar with it. Now, next I want to now switch back to the code and discuss how actually the hash function is programmed, because we're supposed to know how to program hash function. Now, if you look at this code, it's actually, I would say, self-explain. It's not much work. We have to use the doubly linked list, and I think now it's obvious why. Because we're using this. We're creating a data number variable that's part of our hash class, and then we have the size. Now, we have default size 100. And remember here, the size, it doesn't mean the maximum size or maximum capacity, because there is no limit. You're using doubly linked list. The only limit is the limit of your computer memory, and that's it. And other than that, you can grow and shrink the hash according to your need. Now, we have the constructor that will initialize this array, so here it is. Here the constructor receives the size, initializes size, and creates the array data. And this will be like if size is 5, it will create 5 doubly linked lists. If it was 10, it will be doing 10 doubly linked lists, and so on. And then also we have the destructor. Obviously, it will delete that same array. Now notice that we are actually going through the lists values first, invoking the clear function and make sure all the lists are cleaned first, and then after that we delete the data array. Remember, we have two things that we're supposed to be doing: the lists, each one of them has its own nodes, and then we're deleting the array completely. Now the functions that we should pay attention to a lot are actually the compute hash function first, that we explain in detail, and then these functions. Watch the compute hash function. Compute hash function, in the class prototype we have it type T, but if you look at the actual class, watch, we have two compute hash functions written. One that's for integer and one that's for string, according to the example I explained. Now the integer version, we did it, if you recall, value mod size, and also the compute hash, we did it, and also it is it's the same one we just did. I use the size function, and actually it's the same as length, so you could use either one. There is size, if you look at the down, it's supposed to be size, and it is a size function, or length, either one would do it. Okay, so this is a hash function that we explained. Now the thing that we explained maybe just by talk was the insert, delete, and search function. So let's look at the insert first. This is how the insert function of a hash works. Very simple. We invoke compute hash function, store the result in some integer index, and then we just say add tail to that list that is at that index. It's as simple as that. Now the search and delete will simply apply the same idea. So we always do compute hash. Notice compute hash, and then we do the return here in search. Since you're searching, first I identify which list I'm supposed to be searching. Then I am taking advantage of the search function that comes built in the list. So I'm saying, okay, search, for instance, if the index happens to be 2, then data of 2.search. So I'm invoking the search function of the list that exists at index 2 for whatever value I'm supposed to be searching. And if it happens to be there, that one will return true, otherwise it will return false. So whatever is being returned, I'm taking advantage of it in my return function. Same thing applies to the delete. This is pretty much how actually hash is done. If you look in the comments, this is another version of compute string hash function. This is like even better than the one we did here in the demonstration, but it's more difficult maybe to be used for tracing output. So that's why we don't put such a thing in the exam, because it would require complicated, I would say, operations. But this is another one that gives even better distribution. Now, this is how we use the hash in the main. So I can define a hash. The first hash is of type string of size 3, the second hash of type integer of size 4. Then I have, as you can see, two arrays, one array of integer, one array of strings. This is how I can start inserting the values inside the hash. I could apply search, I could apply the delete operation in the same way we actually got used to. So this is it for the hash data structure. I hope, you have the code and the concept clear. If you guys have any question, you could always email me. And next we will be talking about the STL. Thank you for watching.